Hi, welcome to Mathematics with Tom. I am Tom, and today we're going to look at what is called the Heavyside Function. So this is 1.4, and we're going to look at the Heavyside Function. And it's in honor of Oliver Heavyside, and so we use the notation. This function is represented by h of t, and it's also called the step function, and I'll show you why. Well, here is what the function is. It's h of t. Remember, you could make it x, but we're dealing with time primarily in differential equations. And it's 0 when time is less than 0. And it's 1 when time is greater than or equal to 0. So it's this piecewise function. Well, you might think, why is that worth studying? Well, it's actually very clever. Let's just take a graph. Now this graph's going to have some colors going. So I'm going to put my grid down here, and let's do that in this nice white. So make a graph of white. And if you're making one to follow along, give it some space, because we're going to make it not just one graph here, because we're going to see what happens. We're going to empower this graph. So let's graph the first one in the same color. And I should have made my graph maybe come a little bit further to the left here. So let's do that. And then let's graph this. So my initial graph is h of t is here. So it's going to be 0 all the way up to 0. And then at 0, it's going to be a hollow spot there. And then it jumps right up here, jumps right up there. Let me put the number there. That's 1. Jumps up there. And then it assumes the value of 1 at 0. And then it just stays there. That's it. I know, isn't that the craziest thing? And so this is time on the horizontal axis. And we have 1 there. That's the Heavyside function. Well, you might say that looks really dull. And that's what I thought, at least. Maybe you didn't. But what it is this is the way we can mathematically describe turning on a switch. That's what this is. Up to the point where your finger is right underneath the bottom of the switch, and then the light comes on. That's how we can do that. Now, maybe you have a brighter light, then just multiply the Heavyside function by 5 or 10 or however much brighter it is. And now you can even control you could put a dimmer switch on the Heavyside function if you wanted. Now, sometimes though, we need to do something else. Like maybe we want the equation to start at time 0, but we want the Heavyside function or the step function to happen a little later in time. Well, we can do that just as easily, and that's probably best done though in a different color, like maybe this pretty green, so we can see this. Well, what we can do is this. We can take the Heavyside function, h of t, and we can shift it. So this is just the way we shift a graph. This would shift it to the right. If we had plus t, we would shift it to the left. Well, this becomes the shifted version. So it's 0 or 1, and it's 0 up until t is less than capital T, and it's 1 up until t is greater than or equal to capital T. So we're going to draw this now too. All right. So here we go. There's our Heavyside function that's been shifted. This is the green one, so I'm going to overlay this. And let's put capital T maybe right about there. That's capital T. So what happens now is it's still 0. I don't want to draw over my blue, so I'll just kind of try to hover above it. So I just hover above it, come up to T, and now we leave 0. But now we jump up here, jump up to 1. And now this would just continue on in the same way that the blue one does. That is h This is the function h of t minus t, where t could be some shift, maybe 2 or 3, doesn't really matter. And this is this blue one here. This is h of t. All right, so there it is. That's the shifted Heaviside equation. Now you might say, oh, okay, well, that doesn't seem that interesting either. But what about this? What about we turn the light on at time 0? No, let's even be a little bit more creative. Let's do this. Let's turn the light on at time is 1. So after 1 unit of time, could be hour, second, doesn't matter. We turn the light on, but then maybe when we leave the room, what do we want to do? Well, if you're a good environmentally conscious, or even just your own budget, financially conscious individual, when you leave the room, you should turn the light off. Let's see how we can do that now with the Heaviside function. So let's turn the light on and off. So turn the light on, turn, switch on at t equals 1, and turn switch off, oops, at t equals it could be any t. How about capital T? Where t, capital T, is just any number greater than 1. Okay, there we go. Let's see how we can do this. So what we would do is, well, we know, let's just start with this in 2 pieces. The first one is, let's turn our graph on. So let me just make a graph here. Like that, and this. Okay, so here, now let's do this in yellow. So here's 1. This is where, oops, and we need, here's time. We'll give it our, here's 1. All right, so, and, oh, there's 1, so turn it on at 1. I guess my scale's not quite right, but that's okay. All right, so what we're going to do is we'll graph this one in. Let's use this beautiful kind of gold color. So now our first function is going to come up to 1, and we're going to turn the light on. I'm going to turn the light on at 1. So now, and this is going to turn on. This is on. But now hold on a second, because here's where this problem gets more interesting, because what we want to do now is when we get to time t, I want my graph to turn off. I want to turn off. So think about what we have. So I have 0. Here we're at 0. Here we rise up to 1. Now, though, I need to, so here, then we went up to 1. Let's draw a little arrow to keep track. But now what I want to do is I want to drop this down to 0. Well, if I'm at 1 and I want to go down to 0, I would need to subtract 1. So I need to come, let's do this. Here I went up 1. So now I need to come down 1. Well, what do we know is 1? Well, how could we subtract 1 at time t? Well, very simply, we could take this. Our first function is h of t minus 1. That's the orange function. And then we need to subtract 1. So now once t is past 1 greater than 1, so this is equal to 1. And then when t is greater than or equal to capital T, now we want this function h of t minus capital T. Well, what happens? When t is greater than 1, this is 1. Well, if I take this orange one and I subtract this green one, what do I have? I have 0. And that takes me back to the combined function. When I put these two, add these two together, it turns on at 1. And now it turns off at capital T, which could be 2 or 3 or whatever number you want it to. So there it is. The purple function is going to be, we'll just call it h complete. It's my complete T. It's the orange function. It's this h of t minus 1 plus, it's the green step function, h of t minus capital T. And there it is. We've turned something on at time is 1, and we've turned something back off at a later point in time. And that's how we can use the step function. Now that we know what the step function is, the next question should be, what about if that's in a differential equation? Meaning we had some input. Oh, how does that work, and how do we solve that problem? Well, that's what we're going to do next. So we're going to try to keep this in our minds, and we're going to go to the next page, and let's integrate the Heavyside function. All right, here we go. So now you remember, so what we're going to look at now is we have the first order linear differential equation of, let me go, I think this blue is easier to see. Y, actually even easier, I think is this one, is we have y prime equals ay plus, we've said some function q. Q is a function of t. In this case now, q of t is the Heavyside function, h of t, and we're going to just put one in anywhere. So we're going to look at the general case of t minus capital T. And if capital T was 0, then you could go and I'll show you how that works as well. So let's take a look at the most general case. Here we go. Now, we said we also have our solution, and I'm going to write this as of t. So we had our general solution. Let me write this. We know our general solution is of the form. Well, actually, I'm kind of pausing here. One, because I have to sneeze just a second. Oh, excuse me. Oh, whoops. One, because I have to sneeze, and two, because I think, you know what? Let's just derive it. Let's just derive it instead of just reusing the formula, because I think, yeah, memorizing formulas, it takes something away from the mathematics until you know that formula inside and out. Then I think just memorization is not learning. So let's just make sure that, hey, it's in a test, or you're to meet someone in the park, you would be able to say, hey, I don't have it memorized, but I can show you how to solve that. So let's do this. So we're going to solve y prime equals ay plus h of t minus capital T. And notice that this is y prime of t, and this is y of t. And we'll write that in as necessary. So we're going to, again, solve in the same fashion of solve. Let's use an integrating factor. So we're going to look at y prime minus ay equals h of t minus capital T. And we know this integrating factor. This integrating factor, m, is e to the minus at. So let's multiply this through by both sides. So when I do this, I have e to the minus aty prime minus e to the minus atay equals e to the minus at h of t minus lowercase t minus capital T. I'll just call it t for lowercase t, but if it's not t, then we'll call it capital T. That way we don't get too confused when we have the same letter. Now, on this left side, we knew that this can be rewritten as the derivative with respect to t of e to the minus at times y of t. And then what we're going to do is we're going to take the integral of this. So the integral of this from wherever our initial point is, y of 0, to some end point y of t. And let's take the integral on the other right-hand side. This is from 0 to t as well. And notice that this 0 is just normally where we start it, but 0 could just be the letter A, and you could always change numbers accordingly. So we have e to the minus at, or a is not a very good letter. I've already used a. I should use the letter like, I don't know, just another letter. Maybe alpha. There we go. H of t minus capital T. Now this is where I should pick a dummy variable, but we'll be careful. dt. So on the left-hand side, the integral of the derivative is just the function evaluated at the limits of integration. So we have e to the minus at y of t minus, and y of 0, the e to the minus at is going to go away. We're just going to be left with some number y of 0 equals, now this gets more interesting. I think this is why you'll like this problem so much. Now, think about this problem. And I'm going to go over to my previous screen. So let's turn the screen off. Let's return to our graph here. Well, and we have to do a little thought process. If we're going to integrate, we're working here on our green, this initial green function. So we are, we are back here on our initial green function. Here's h of t right there. And the question is now how in the world do we integrate e times h of t minus capital T? Well, look at this. From 0 to capital T, this is just the 0 function. And the integral of 0 is just 0. But what we do have to integrate is from capital T onward, because there h of t is 1. So really our limits of integration then are from capital T out to t. Those are our limits of integration. With that in mind, let's go back to our other screen and let's solve this. So now this is really the integral. This becomes now the integral from from 0, oh, not from 0, goodness, from capital T to lowercase t of e to the minus at times, and I'm just going to write this so that we can remember what just happened, h of t now is just 1, dt. Well, we can let's integrate this. So on the right-hand side, this becomes e, oops, that's not correct. It becomes minus 1 over a times e to the minus at minus e to the minus a capital T. There it is. Now we can keep solving. So I'm going to have to bring the equation up here. Let's finish this now. Let's put the initial condition onto the right-hand side. This is e to the minus at y of t equals, just making sure I'm not off my screen here, equals y of 0 minus, now here this looks a little interesting. I'm going to, well, you know what, we'll fix it later. Minus 1 over a e to the minus at minus e to the a capital T minus a. There we go. Let's take care of this now. So now what we need to do is we need to isolate y of t. So we can do that by multiplying both sides by e to the at, positive at. So multiply this right side by e to the positive at. So we're going to distribute this e to the at to the y of 0, to the e to the minus at, and to the e to the minus a capital T. So on the left-hand side, I have y of t equals, then I'm going to pick up a y of 0, e to the at, minus 1 over a times e to the minus at times e to the positive at. Well, remember, you just add the exponents. Well, that's just e to the 0, so this is 1. minus, and I'm going to write this one out so we can look at it. This is minus, I have an e to the minus a capital T plus a lowercase t parentheses. Let's do some housekeeping here. I'm going to write y of 0, e to the at. Then let's distribute the minus sign. So we're going to have a plus of 1 over a. And then, and we're going to clean this up. But let's clean this up by the e component, e raised to the, let's see, we have a common factor of a. So I'm going to take out the a. And that's going to leave me with a positive t minus capital T. Oh, and look at that. That accounts for the shift. That's the shift. And then minus 1. Because remember, we factored out that minus sign, so I just switched them so it looks prettier. And oh, that's it. That's it. But now notice what this problem does is there's a piece in here we need to add, is remember that this function here. So in this, we'd say this is for t greater than or equal to t, because remember this piece right here is just 0 when we started out. The one last thing is, let's just think about what this equation did. Let's think about how this all comes together. And here's how that works. Is notice this. Let's look at our original problem when we wrote it out. It was the equation, the integral from y of 0 to y of t, derivative with respect to t, of e to the minus a t y of t dt. And then over here, what if I had this piece, the integral from 0 to up to t? Well, remember that this integral here, and then we'd still have a e to the minus a t h of t minus capital T t t. Well, when we had this piece, this whole thing was 0. And so what this means then is that it's really a piecewise function. So really y of t is equal to just the null solution. So it's equal to y null for t less than capital T. And the null solution is just this component right there. This is y null. And then from after that, it's y complete. And y complete is this, what we have up here. This is y complete. So y complete for t greater than or equal to t. So the answer for integrating the step function actually creates a piecewise differential or solution to our differential equation. I hope that helps, and thanks for watching.